Hello and welcome back to STEM Online Academy. It's STEM Online Academy, for those of you who don't know, who are new viewers or new subscribers, is a channel about uh, advanced mathematics and physics concepts, right? Specifically, interesting topics in these fields. I'm going to talk about also problems, interesting techniques and problems to solve uh, math, physics, or even some applied physics and engineering problems using a three tier approach that I came up with, which is by using one, uh, making sure that you understand what it is that you're looking for, right? Step one for my problem solving technique, right? So you want to make sure you're understanding exactly what you're looking for and how to translate that into step two, which is a geometric model, right? Of either the physical or mathematical phenomenon. Because if you understand what the problem is, you should be able to create a drawing. The drawing helps you understand give you more of a conceptual understanding of how to solve the problem, right? Or if it's an equation, the equation is even easier to model because uh, you know graphing techniques from your math classes, right? So if you know the equation, you're able to graph it, right? So whether it's a graph or a geometric model, right? Uh, from there, right, once you have the graph or geometric model, you can then extrapolate that into a hopefully a mathematical equation that makes more sense, right? Because the point of the drawing is to make sure that one, well, first off, it brings the problem to life and makes it not as boring, especially if you use simulations like me. And number two is because it helps put it into an applied focus, right? What I mean by an applied focus is hopefully by having the drawing in front of you, you can make sense of what you're looking for, right? For instance, a classic example to, you know, help convey what I mean is, for instance, let's say you're looking for the area of a curve, right? All right. So let's say, for instance, I'll draw a curve here. All right. So let's say you have a curve like this. I want to use some different colors here. Okay. So let's say you have a curve like this. Okay. So it's a cubic equation of some sort. Y equals x cubed. Okay. So this is y equals x cubed. Okay. So y equals x cubed. Okay. Now let's say if I wanted to figure out the area, right? So the area from 0 to, let's say, 1, for instance. Okay, so something like this. If I wanted to calculate, right, the area from 0 to 1, the interval, okay, so let me shade it in. Okay, from 0 to 1, then my area, without even calculating it, would you think the area should be positive, negative, or 0? It would have to be positive, right? Because the area under the curve from the bounded region from 0 to 1 is on the positive part of the x-axis, okay? So it has to be positive, all right? Okay. This is a classic example how whether it's the easiest or the hardest problem, having a graphical or geometric model helps you make sense of the problem, okay? And then from step 2 to step 3, uh, you want to then mathematically solve it with step 3. Step 3 is the easiest because you're just applying a mathematical method. Now, not all mathematical methods are easy, right? Okay. Especially for my book. My book is really challenging. But uh, different types of mathematical methods can be deployed and help you solve a problem. Okay. So that is always my unique perspective on how to solve math problems. Usually it works. It may not always work. It depends who's using it, right? Okay. Anyways, so let's get back to it. So for new viewers, for viewers who already know me, you've seen my videos. I'm either talking about math concepts in general, for undergraduate, graduate, or research individuals. That's my niche target. Uh, and more specifically, especially with my new book, as you know, Advanced Integration Techniques, this book even narrows it down even more. Okay, where we're going to be looking at advanced integrals and their applications, right? If you've been keeping track, we've been doing a lot of problems from this book. For those of you who already know, for those of you who are new, I hope you're good at integral calculus and linear algebra. That's all that's needed for the most part so far what we've been doing. Okay, so we're going to continue doing some problems from the book. All right. So let's get started. Today we're going to be looking at, okay, um, how big is a sphere in 10-dimensional space? Now I know you're thinking, how is that possible? You must be asking, Jason, how are we going to draw or visualize something in 10-dimensional space? Guess what? I can't do it either, but technology can. Okay, so I'm going to bring up a simulation soon and show you a simulation of the geometry in 10-dimensional space. Okay, all right, to the best of my ability. So let's get into that. And as you know, this is, if you've watched my live shows, I also have live shows too, weekly, twice a week. You watch the live show, this will be pretty close to the live show, so you don't have to watch this. Well, unless you want to see something very interesting at the end. There's a very interesting um, proof that I want you guys to do if you watch the live show. Okay, so that's what we're going to be talking about. All right, so first, I'm going to talk about why your intuition fails, in 10-dimensional space. Okay, so intuition fails in 10-dimensional space because first off, it requires something called, um, well, we don't have, as humans, we don't have the visual capacity for higher dimensions. Okay, we can speculate about higher dimensions. We know that there's uh, dimensions that we can't see, feel, or touch, or smell. Okay, what do I mean by that? Well, an example, right? Think of three-dimensional space, length, width, height. Okay, so if you, let's say you had a rectangular prism, okay, you can see it, you can feel it, you see all three of the dimensions, it's right in front of you. But if it was four-dimensional space, that's when things get very complicated, right? Even three dimensions, people have trouble, even though it's rather straightforward. But as you get three, four, five, six dimensions, things become complicated, very complicated. Okay, so we don't have in our neural wiring a mechanism for that. Okay, all right. So we can mark off our checklist. That's done. Next, we won't get to this right away. Okay, we won't get to part two right away. I'm going to jump. Okay, actually, yes, we can get to part two. Let's get to part two. So we're going to use the Gaussian integral to compute volume. Okay, you should know what a Gaussian integral is for those of you fluent in integral calculus. Okay, so we're going to look at solving the following. So what do I mean using Gaussian integral to compute volume? How does Gaussian integral relate to volume? So it's going to relate to volume using this expression. I've already talked about my live show. Here I'm going to go a little faster, but volume of n, right? To compute, this is computing the volume in n-dimensional hyperspace. Okay, that's what we're looking for. So volume of n and n dimensions is equal to pi to the n over 2 power divided by the gamma function of n over 2 plus 1. Okay, and we're looking specifically at n equals 10. Okay, so at n equals 10 is what we want to calculate the volume for. All right, so the way to do that, okay, is this very, very straightforward. Okay, we're just going to do the following. Okay, maybe I should give you a bit of a formal understanding before we compute it. All right, so let's look at, yes, let's talk about a formal understanding of what this means. Okay, So it's one thing to know the formula and compute it. It's very straightforward. It's just basic computation and algebra involved. But for those of you who are new, uh, this problem, okay, we were just finding the volume of an n-dimensional hypersphere, okay, of radius r. That's what we're doing. Okay, I think that's straightforward. Okay, hypersphere because we're talking about dimensions that are pretty crazy. Okay, greater than 3. In one dimension, so think of it this way. There's an interesting general pattern we can deduce here. One dimension, we have a line segment. Okay, so in n-dimensional space, n-dimensional hyperspace, right? If you had it only in one dimension, we'd have a line segment. I think that's very straightforward. One dimensional lines, extending a distance capital R in each direction radially, right? Okay, such that the length would be v1 equals twice 2r. Okay. However, if you had it at n equals 2, okay, then it will be an area of a two-dimensional space. The area of a two-dimensional sphere in reality is a circle. Okay, so v of 2 is pi r squared. Right? Okay. And you can see that we have very quickly here a continuation, right? There's a general pattern that can be deduced. Okay. Um, I've labeled everything here. Volume of a sphere will be 4/3 pi r cubed, obviously, right? As you can see here. So n equals 1 is a line, n equals 2, circle, n equals 3 is a sphere. Okay, and what we can get to, I talked about this in my live show, if you watched the live show, is how we got to v of n of r, okay, which is capital K, which is a constant, times capital R to the n. K is a constant, which is scaling pi, okay? K is there's a reason why I have K here and R. R is the radius, and you can see that there's a pattern from one-dimensional space, R to the first power, two-dimensional space, R to the second power, three-dimensional space, R to the third. That's why I concluded that it's K times R to the n, where K is a constant, okay? So we can say that Vn of R is equal to K subscript n minus 1 times R to the n. I hope that is sinking in, all right? Shouldn't be anything that complicated so far, all right? So think about what I'm saying here, right? If I have a general pattern of V of R, Vn of R, okay, we have K, there has to be some constant K in front of the R, because you see here, look, 2 is a constant in front of R, and it's pi, and it's 4/3 pi, where K is an arbitrary constant, right? There isn't a pattern to K, but we know that the pattern in general is a constant times R to the n. R is more pattern recognition because it goes from R to 1, R squared, R cubed. Okay. All right. So we've got that, and we can more generally say K to the n minus 1 by R to the n doesn't matter. All right. And here, if you don't know, it turns out K subscript n minus 1 is the unit volume. All right. So it's the unit volume of the sphere. Okay. You may not know that. A lot of you who even know about Gaussians and gamma functions and stuff like that, will not know this specifically. Okay, and that's where my book can help talk about very interesting things here that for those math enthusiasts will find very, very interesting. Okay, especially if you like interesting topics in analysis plus calculus. Okay, so at k subscript n minus 1, we have k of 1, and this is equal to 1. This is for a unit volume, a ball of unit volume of radius r. That's what this k of 1 is. Okay? In other words, you're thinking like, well, how am I coming up with this craziness? Well, like, am I doing something? It's an assumption that you have to make when it comes to n-dimensional hyperspheres. All right, so let that sink in. Okay, so let's start calculating some stuff. We want to calculate the volume at n equals 10. Just use the volume formula, pi to the n over 2, all over gamma of n over 2 plus 1. All right, very straightforward. Plug in n equals 10 dimensions. You'll notice that we get v of 10 equals pi to the 10 over 2, divided by gamma of 10 over 2 plus 1. And then this v of 10 will be pi to the 5th, all divided by gamma of 5 plus 1. Okay. From there on, we notice that we get v of 10 equals pi to the fifth over gamma of 6. Now, for those of you who know the gamma function, how would you compute gamma of 6? Gamma of 6 turns out to be gamma of p equals p minus 1 factorial. The gamma function can be computed very easily using this formula right here. Okay, I mean, you can use the gamma function interval, but this makes it more complicated and longer and may not even be feasible, right? Just use this. It's straightforward. Get to the point of calculating it directly, okay? So gamma of p is equal to p minus 1 all factorial, where p is the number inside of the gamma function, okay? You should know factorials, all right? So having your p being 6, okay? So v of 10, right, would have been pi to the fifth all divided by 6 minus 1 all factorial. Okay, so 1 all factorial, and this becomes pi to the fifth over 5 factorial. Okay, so we got that. This should be so far straightforward. Okay, and then 5 factorial should be 5 by 4 by 3 by 2 by 1, which is pi to the fifth over 120. Okay, and if we were to put that in a calculator, we get 305.244 divided by 120, which is 2.54. All right. So the point of this calculation is to verify that the volume is 2.54. Okay. So we figured out that the volume of a 10-dimensional 10-dimensional sphere, 10-dimensional hypersphere is 2.54 units. Yeah, right. Right. So it's very interesting how you can calculate volumes, and you calculate volumes of geometries that don't even correlate to 3 dimensions. They could get to arbitrary number of dimensions, right? Like n-dimensional space. It doesn't matter if we had 100 dimensions or 1,000. Okay, we would be able to calculate it using this formula for the hyperspheres. All right, so we've got that. All right, I think that's pretty interesting. So if you're like interested, like as I said, calculus or geometry, you'll find this book very interesting, especially if you know integral calculus and linear algebra, and you have a solid understanding of it, and then you want to take it to the next level and learn concepts that are beyond your reach. This is the book. All right. So, all right. So we got the volume. All right. All right. So the next thing I want to discuss. Okay, let's go back here. Okay, is why the gamma function, right, secretly controls geometry. Why does it control geometry? Just realized it's like, shouldn't say controls geometry, but is embedded in geometry. Yeah, I think that's a better word. Yeah, embedded in geometry. So the reason for that is because if we go to my diagram here, right, first off, okay, based off our simulation, it will tell you why our the gamma function is embedded in geometry, right? You can see that we have a 10-dimensional space, right? 10-dimensional hypersphere, okay? And you can see that this hypersphere, right, actually um, is actually embedded in nature, at least in space, okay? So if you have, as I said, this hypersphere here in 10 dimensions, right? So if you have a regular sphere in 3 dimensions, okay, that's taking a circle, all right, and then putting a 2-dimensional projection on the XY axis intersecting that circle, and then it gives you a sphere, right? Now think of multiple 2-dimensional projections, right? 2-dimensional projections of circles. That's what like multiplied by 5 will give you 10-dimensional hyperspheres. Okay, that's what this is showing. So if you look at it, it looks really, it's a really interesting, interesting concept. Okay, so this is the visual simulation of this function, the volume as a function of n. All right, so let's get back to the board. So let's get to plotting volume versus dimensions. So if you go plotting volume, let's go back. So again, I like to have this. I use a very unique perspective that hopefully is both fun, interesting, and also conceptually better for you to understand math. Okay. All right. So we're going to look at the graphs. Okay. And also why I did that calculation of the volume of 10-dimensional hyperspace. I'm going to show you how my calculation by hand matches the simulation here. Okay. If you look down at 10-dimensional space, with the 10-dimensional space volume formula at n equals 10, right? Pi to 10 over 2 divided by gamma over 6, you get 2.55. We found 2.54. It's just a 0.1 difference. Okay? That happens. It's just a matter of decimals, but that's it, right? So you can see we almost have it exactly matching the volume there. Okay. And then also, I wanted to show you this, okay, a comparison. You can see that we have the volume, right? Volume across the dimensions. Okay, so we have, so you can see here a bell curve. So we're taking our 10-dimensional sphere, and that's in hyperspace, which is complicated to visualize and stuff, and putting each of these two-dimensional projection circles concentric as concentric circles over here, right? From 2D, 4D, 6D, 8D, and 10 dimensions, right? Radially going outwards, okay? That little dot, right? That little dot there, right? These dots, okay, are actually, the points of those two-dimensional spaces are actually just bell curves, okay? Bell curves inside those circles there, okay? So it's very interesting how we can break down not only go from having the function, graphing the function, and then breaking down that graph piece by piece by piece, right? Using simulations or maybe even hand-drawn models. Okay, so you can see here we have a bell curve, right? So in reality, we are calculating to calculate the volume of an n-dimensional hyperspace in 10 dimensions, or any n dimension, we're actually calculating the Gaussian integral. Why? Why are we calculating a Gaussian integral, even though I didn't use any integrals? Because the gamma function is embedded in geometries, right? As you can see there, the proof is in the pudding, is in the formula. The gamma function is in the equation there. And since uh, we, we've shown that we have a bell curve, right? A bell curve within our 10-dimensional concentric circles to find the area, because we have to calculate the area underneath the curve, pretty much just using Gaussian integration. So Gaussian integration is related to the gamma function in a way. Okay. All right. So that's what I wanted to show you. Okay. And I think it's very interesting. It has a lot of interesting applications. The gamma function. All right. Right, so to have a more detailed analysis of all this, you should check out my live show. Even though it's already done, it's no longer live, but you can check it out on my channel. Okay, so the last thing I want to discuss really quickly that wasn't added to the live show is, for those of you up for a challenge, is to try and do a derivation of the volume of n-dimensional hyperspace. Okay, so I want you to prove that v of n, right, is equal to little pi to the n over 2 power divided by the gamma function of n over 2 plus 1. Okay. This is going to be somewhat tricky, but for those of you who are up for a challenge, like mathematical challenges, well, this is the place to be. Okay. I'm going to give you some hints here. Okay. First off, in the proof is that v sub n of r is equal to r to the n times nu of n. How do I know that? Well, as you already know, there was a certain pattern that we figured out that Vn of r is equal to k by r to the n, or k in this case, it doesn't matter what I call it, k and or mu sub n is some constant, okay? Or some constant times the radius to the nth power, okay? So we figured that out. We also know that the volume of a hypersphere of unit radius, capital R, uh, has nu sub n equal to capital V sub n of 1, right? That's where the volume of a hypersphere of unit radius R is, okay? And what you guys need to do is to see if you can calculate the volume of any closed solid, which is this integral, right? Okay, so what I want you guys to do for homework is to try this problem, okay? Let me know how it goes in the chat. Um, Write anything in the chat, uh, whether you want to take up this problem, whether it's something that's not related, as long as it's related to math and physics, you can ask me that. Tutoring, anything that you want to discuss, you can put it in the chat. Okay. All right. So try and compute this. This requires quite a bit of a little bit of ingenuity, but uh, for the full derivational roadmap, you can also check out my book. Okay, that will be either in the description. I'll probably put in the description in the chat, or yeah, I'll probably put in the description in the chat if you want to know more information about my book and get a copy, or if you just anything else doesn't matter. Okay, all right. So that is that is it for today. Hope have a great evening, and I'll see you guys next time. Bye for now.